just gonna go ahead. So as most of you already know me, my name is Behnam Askarian. You can call me Ben. And this semester we're gonna have digital design fundamentals. My email address is baskarian@wtamu.edu. My office is in ACS 221J. And my office hours are Monday, Tuesdays from 3 to 5 p.m. I'm also available Monday, Wednesdays after 10:30 a.m. So if you want to stop by my office, you can come over on Monday, Wednesdays as well after 10:30 a.m. My office number is 806-651-5248. If you have any questions, just please call or send me an email. If I don't answer a call, I'm probably not in my office, I'm in a class. You can email me at any time, and I will try to get back to you as soon as possible. For this class, you don't have any required materials. You only have a recommended book, which is the Digital Logic Circuit Analysis. You can get the digital logic design by Morris Mono. And you may just need a calculator. For the lab, I would provide all the parts and equipments that you need, so you don't need to get anything. And as I mentioned, you're gonna have a simulation in the 3rd or 4th week to simulate the logic circuits that we're going to work on. And then after that, we're going to have hands-on experience and go to the lab and build those logic circuits. For the online students, I will provide them with a simulating tool, and there's an alternative for them to do their labs. For this course, the topics of this course are the number system, conversion methods, Boolean algebra, different logic gates, and circuit minimization, flip-flops, latches, shift registers, and so on. The objectives of this course are to understand digital electronics, terminologies, and learn about number systems, as mentioned, Boolean algebra, and eventually the second book after digital design, which is the first book from Morris Mono, is about computer architecture. So this is actually a basis for learning the electronics of a computer, learning how a microcontroller, microprocessor functions, how a CPU works, how different memories work, like RAM, ROM, read-only memory and random access memory, different types of memories. How do we address these memories, the bus system, multiplexers, decoders, encoders, so internal components of a computer, the hardware part of a computer. And you already know about the ABIT, so these are the ABIT learning outcomes. The course evaluation, this is, by the way, already on your, I think, yeah, I've already posted this. You can find it. And for the evaluation of this course, the homework is going to be 5%. The final project and the lab work would be 20%. So 10% lab work, 10% final project. And for final project, you would build an actual circuit with the logic gates in it, like a multiplexer, decoder, encoder, flashlight, something like that. Or any other circuit you want. You can just bring your project and build whatever you want, as long as it has a digital circuitry component to it. You can build any circuit that you want. The student involvement, which are the quiz, for those who already had a class with me, it's going to be the random Kahoot quiz that we have. That's going to be 5%. for the online students, it's after I post every video, you're gonna have a 1 or 2 question quiz after that, which that is gonna be the participation and the student involvement. You're gonna have 2 midterm exams. It's gonna be 20% each, and a final exam. So the grade scale, A is 90 to 100, B is 80 to 90, C is 70 to 80, D is 60 to 70, and below 60% is F. And I think if you get a D, you have to repeat this class. So the final exam, it's going to be a comprehensive exam. You're going to have it from the, it's going to cover the entire materials. And it's going to be, I think it's already on the calendar of the university, the date of the final exam. For the homeworks, when I post the homework, you usually have 1 week to 10 days to complete and submit your work. As soon as I post the solutions, I don't accept the homeworks anymore. So usually 7 days to 10 days, so a week to 10 days. And you can read through the policies. Oh, one thing that is important is about the use of generative AI. Using ChatGPT and chatbots and AI is strictly prohibited. And the reason is I want you to develop critical thinking skills. You may think it's going to help you right now, but when you want to go and interview for a job, for example, if you want to apply for a job in NVIDIA, which is actually the second book, as I mentioned, is for computer architecture and designing GPUs and so on, then you won't have access to a generative AI tool. So it's better to learn the material. It's not very difficult. Digital design, I think, is actually one of the easier courses in electrical engineering. So it's not that easy, but it's relatively easy to learn, and you need to practice. As I mentioned to my students before, engineering, especially electrical engineering, is not like English major or philosophy major that you can open a book and just memorize it. Try to solve problems yourself, and it's through challenging yourself and getting frustrated by some examples you can't actually learn these materials. So again, no use of generative AI. It's strictly prohibited for solving quiz, homework, exams, anything. And we have the different statements here. Please go. I think you already have read these in your other classes. This is common between this part, between all your other classes as well. And for the tentative calendar, for the first week, we're gonna have introduction and number systems and codes. Second week, it's gonna be algebraic methods for analysis and synthesis of logic circuits. The third week is going to be simplification of switching functions. And we're going to have a review for exam number 1. And I would highly recommend that you join my review classes, because a lot of the materials that are going to be on the exam would be covered on the review exam. I'm going to solve a lot of problems that are very similar to the exam. Then we have modular combinational logic gates and combinational logic gates, and combinational logic gate design or circuit design. Then we have sequential logic gates or sequential devices, and modular sequential logic. Review for exam number 2, and after that, a little bit more about sequential logic, like shift registers and so on. And then we're going to have a review of the final exam and the final exam. Okay. Before I start, if you have questions at any point, if you can't understand my accent, or I'm talking too fast, or looks a little confusing for you, just please stop me at any point and ask your questions. maybe your question would be your friend's question as well in the class. I'm comfortable with answering your questions 100 times. And yes, please, at any point, just please stop me and ask your questions. Do you have any questions from the syllabus? No? Okay. So let's dive into the class. I already posted, I think, the materials is, can you see the materials on? You can see it. Yeah, okay. So I've already posted the PowerPoint slides. You can find it. So for today's class, we're going to start with chapter 1. The outlines of chapter 1 in the first class are going to be digital systems and binary numbers. We're going to learn about digital systems. What does a digital system even mean? Then we're going to go through binary numbers. After that, we're going to start with number-based conversions. And after that, we're going to go, I think we can cover the first 2 parts today. And after that, we're going to do octal and hexadecimal numbers and complements, which is probably going to be next week. Signed binary numbers, binary codes, binary storage, and registers. And finally, binary logics. These are going to be everything that is, well, it's covered in exam number 1, chapter 1. Okay. So what is a digital system and what are binary numbers? So we are in the digital age and the information age. Digital basically means it's a digit. It's comprised of digits. So we have discrete signals and we have continuous signals. Sometimes the digital circuits are also called discrete signals as well, because they are not continuous like analog signals. So we have analog and digital, and I'll explain what's the difference between them. So we have, this is a little bit of, introduction. We have different digital computers. We have general purpose computers, and we have many scientific, industrial, and commercial applications for that. One example would be PLC, which are the programmable logic circuits, which usually are used in industries, for example, in a factory or in other industries. And we have digital systems like telephone switching exchange, digital cameras, electronic calculators, PDAs, digital TVs, or laptops, phones, tablets, etc. All the communication systems that we have, most of the communication systems we have right now is digital communication. We have analog and digital communication. Most of the communication that we deal with right now is digital. We still have some analog communication systems like AM and FM as well, signals, but mostly they are now replaced by digital, like 5G and 6G that you have on your phone is actually use a digital communication system. And then we have the discrete information processing system, like for manipulating discrete elements of information. For example, we have 1, 2, 3, and ABC, and I'll explain more about this. Now, what is an analog or continuous, and what is a digital signal? So an analog system is the physical quantities or signals that may vary continuously over a specified range. Everything that you see in nature, everything that we hear or see is analog. We don't have anything as a digital signal. One example is going to be sound. So any sound that you hear, it's basically an analog signal. And what we do is we convert that analog to digital to be able to process it better. And I will give you some examples of why we do that. So what are digital systems? They are the physical quantities or signals that can assume only discrete values, and they have greater accuracy. So on the bottom, you see 2 different signals. On the left, we have an analog, And on the right, we have a digital signal. Okay. As mentioned, analog signals could be any voice that you hear around you, or you can just move a magnet very fast and create an analog, a microwave, analog signal. One other example is going to be the microwave that you have in your house and creates some analog waves. So all of them are continuous wave. If you have a oscilloscope, you can monitor that as well. They are continuous. They are not discrete, and they change with time. Okay. And usually we have a maximum and minimum amplitude for them. I'm going to call this XM. That's with capital M, and XM with lowercase m is the minimal. And also, we all have a period, and from that, we can calculate the frequency. So we have a frequency. All these signals have frequency, amplitude, and a phase that we can shift it. We can start with 0 degrees, 90 degrees, and so on, which you're already familiar with. In a digital signal, we have the frequency, we have the maximum and minimum. The only difference is here we have discrete signals that can only assume certain values. So for this example, our values could be only, for example, let's say this is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 volts. So we don't have, for example, 1.5 volt here, or the value of 1.6. But in the left one, we have 1.5 and 1.6. So which one has more information? The one on the left, okay? But why do we even use a digital system? By the way, we can transfer data using both of them. You may think we are missing a little bits and pieces in the second one, but in some cases like voice, a human ear is capable of hearing anything between 20 hertz and 20 kilohertz, for example. Anything above that, we are incapable of hearing. So even if you increase the frequency or the bit rate, what we call, we have different bit rates as well, like 64, 128, and so on. The our hearing system is not able to differentiate between higher frequencies and lower, anything higher than, like, 50, 60 kilohertz or so on. And it's different from human to human. Some people are capable of hearing a wider range of frequencies. Some people are, usually they are limited to a lower range. I always give an example. This is a small joke, but like women sometimes hear a wider range of frequency, and men are more narrower. So sometimes when my wife speaks with me, I tell him it's not that I don't listen to you. I can't hear, because my brain is limited to a narrower band. But the thing is, and it's the same for vision as well. Some people are capable of differentiating 16 million colors. Some people we can't even differentiate between green and blue. So it's different person to person, and it's different for when you get older or younger. That actually frequencies tends to shift as well. Now, as I mentioned, every signal that we have in nature is an analog signal. But we want to convert it to digital. Why do we like to convert that to digital? Why don't we just keep it as an analog signal? And everything before 1990s and 80s, everything was analog. We just switched to digital like 20 years ago. And actually, there's an interest to going back on analog circuit design right now as well. For some applications, analog signal processing works much better than digital. But like 90%, 95% of all of the systems that we have, like processing, communications, are digital right now. Can you think of a benefit of a digital signal compared to an analog signal? Just by looking at this. Why do you think we even use a digital system instead of an analog system?
Wider range.
Yes, so one thing that we can do with, yes, perfect, that's a great example. One thing that we can do with digital signals, it's much easier than analog signals, is what we call signal processing, digital signal processing, DSP we call it. So processing a digital signal is much easier than an analog signal. So for example, imagine this, the analog signal on the left is a sound signal, and you're recording a music, track or something, and suddenly when you're recording your voice, something falls down and you have a noise in the system. And imagine this one is our noise, okay? I'll show it with N. If I want to get rid of this noise and filter the noise, for an analog system, we have to use different types of filters. We may use a notch filter, and then we don't know the exact frequency, so we have to shift that frequency. It's going to be very difficult. But if I convert that to a digital, then I would have one dot here and, for example, one here. And through digital processing, I can say everything, for example, above this and everything between these two, you can just cancel them out, or anything between these 2 points, sampling ports. So, or I can just simply put a code and, get rid of those noises. It's very easy to process an analog signal. I'm sorry, digital signal compared to analog. So that's the reason, one reason that we convert analog to digital is for processing. It's much faster. You can put a fast Fourier transform, what we call an FFT, put a filter and get rid of all the unwanted signals. This may not seem like a big deal when you have a voice or a soundtrack, but when you go to 3D, like an image, then image processing, it's going to be a nightmare when you do it in analog. It must be done in digital. And now I go through an example of how a digital picture actually works. So one reason is for filtering, manipulating the signal. It's much easier than in a digital system than an analog system. So for this particular one on the left, if you want to filter out this part, you actually need to build a hardware for it. You need to build a circuit, which usually could be like a high pass filter, something like this. But for the one on the right, or a bypass or a low pass filter or something like that. But for one on the right, you don't need any physical components. You don't need a different circuit, a capacitor, inductor, resistor to build that. And actually, this is a passive high pass filter. You need an active high pass filter because you don't want to lose any of the amplitude in the signal. You don't want to actually weaken the signal. So you need an op amp on top of that. So you're adding 20 components to just get rid of this piece. But if I use the digital signal processing, it goes through a computer and you can simply write a code and you can get rid of it. So it's much easier. You can update it. You can, upgrade your software over the air updates and get rid of a specific. And it's much easier than doing it analog. So this is one reason. Another reason is for data transmission, okay? For data transmission, when you want to compress a signal, so all the data that you see on your phone that goes through, that you get from internet or all your communications, they are all compressed first. And we have different formats. So MP3 is actually a compressing format, or MP4 or JPEG. All of these are designed to compress the data, because if you want to send a picture, normally it would take 200 megabytes of space. If you compress that picture, you're just gonna have 1 megabyte without ever comprising the quality. So one other way is for compressing the data that we use the digital design. And let me give you an example. So instead of sending the whole signal on the right, for the analog, we don't have any options. We have to transmit it. And by transmitting, you have to send different levels of voltage at different times. But for the right, I can say this, and the ones that have the same amplitude, okay, like these and these and these, I can say at 0, 1, 2, 3, 4, 5, 6, 7, 8, and so on. So I can say at 0 and 1, 2, 3, 4, 5, 6, 7, 8, 9. And 9 second, I have an amplitude of, let's say, 3 volts. And at 1 and 8 second, I have an amplitude of 4 volts. Do you get me? So I can compress it. Now, instead of sending every single voltage, I can pair them, and immediately I would have half the space. And I can do this over and over. So one important advantage of a digital signal is the ability to compress it. So noise reduction, processing, and compression, that's very important. And imagine you have let me give you another example. So I'm old enough to remember those video chats that sometimes froze. I don't know if you had experience with them, but when you video chat with somebody, I don't know, 15, 20 years ago, and you have the dial-up system, if the person was sitting still, you would see a continuous image without any interruption, or the person wouldn't get frozen. And the moment the person stood up or someone walked behind it, you would immediately see that the picture is glitching. And it's the same thing for new video chats as well. The reason was this, actually. So those type of video chats, and still they use them as well, use a type of compression that looks like this. Imagine we have a person or an object, let me put an object, in the middle of a white screen. And I want to transmit this data to a receiver to see this, okay? What I can do if I have a digital signal, I can just send this object in the middle, and I can tell the receiver that everything else in the background is white, okay? So I could say that I have a triangle which is red in the middle, everything else is white. And because of my background is stationary, I can just send that picture once and send the moving object every 5 seconds, 3 seconds of refreshing. So now instead of sending the whole picture, I just send like 1/20th of the picture. So I send the background separately, and then, but what happens if another objects move? Then the computer must send all the background again. So that's the reason you see a glitch in the picture. So one way, again, this is another example that they use, and they use it for pictures and videos, is the ability to be able to compress. And I'll explain how we actually use a digital signal to show pictures as well. So now that we learned the benefits of a digital signal, how can we convert a analog signal, the left one, to a digital one on the right? How can I go from the left one to the right one, from analog to digital? And this process actually has a name as well. We call it ADC, or analog to digital converter. So how can I convert an analog signal to a digital one? Perfect. Well, it's what we do is called a sampling. Thank you so much. So we can sample at each time. So I can say I'm going to sample at 0 seconds. Then I'm going to sample at, for example, 1 second and 2 seconds, 3 seconds, for example, so on. And this sampling rate is up to us. I can have a higher frequency, more samples, or I can have a lower frequency. So this is an example of one sampling frequency. I'm going to do it with the green one. Or I could do my sampling frequencies like this. I can just have 2 samples here. Something like this. So, and this is called a sampling rate. The higher my sampling rate is, you're going to have more accurate data, but you're going to consume more. You're going to have, you need more memory. And when you're going to transmit it, you need a higher bandwidth. Okay, because you have a higher frequency. The lower the sampling rate goes, you will need less data, consume less memory, but you're going to lose some information. Sometimes that's important, sometimes that's not important. One example is when you watch YouTube, you're on 5G, you want to change the quality. You can go from 380 pixels to HD or 1080 or so on. So what that does is actually it's changing the sampling rate. So instead of having 20 pixels per inch, you're going to have 5 pixels per inch. That's the way. So you're going to have a lower quality, but you don't care about the quality that much. You maybe watching a podcast that you don't care about the video quality, you just care about the sound quality, okay? And when you're limited in your speed, especially internet speed, it's better to have, a faster speed than a higher quality. Sometimes you need fast speeds and high quality, like, I don't know, online gaming or something like that, video chat. But sometimes you just okay with the lower, and you can lower the sampling rate like this. So by sampling that, now if I want to show the green one would look like this. Actually, you would have, like, I'm going to do it smaller on the top. So you're going to have something like this. Okay. This is going to be your green one. So if you can see, if I connect them, you're not going to have the exact shape as the original one, but it's going to be very close. Now, for sampling, by sampling, we can convert an analog signal to a digital one. Now, how can I go from a digital signal back to an analog one? So now if I have a digital signal, which I have in the left one, and I want to go to an analog signal, how can I do it? And by the way, this is digital to analog, and we call it digital to analog converter, or DAC. Yes, smooth it, or in other words, you just can connect these dots together. And what we build is actually we can build the original analog signal. Yes, exactly. Yes, perfect. Yeah, just piecing together, that's bridging the dots, just connecting the
So analog to digital is basically like taking it apart and then putting it back.
Yes, exactly, like a Lego that you take apart and put it back. So how do we do the sampling? Now let's go to the hardware part. What circuit that we use? So we usually, if we have an analog signal, we can simply use a switch. And from that switch, this is V out. You can have a load or not. So this is your analog signal, and you have a switch that is switching with very fast rate. I'm going to show it with just S because I can't write. I don't have space to write all. So you have a switch, you just, depending on the frequency, if you want to do it 10 times per second or 100 times per second, you just close and open the switch, okay? So sampling is as easy as that. You can just use a switch, and you can actually use an op-amp, different type of things, but we use different type of parts for that. You can do it with a computer, just with a relay, or depending on the voltage that you want, the frequency that you have. The principle is very simple. You have a switch, you just rapidly turn it on and off. So when you close the switch, you're going to have a V out, which is a sample. When you open it, you don't have voltage. So you're going to just open and close the switch. Okay. Is it clear, or do you want me to explain more? Is it clear? Okay, so imagine you have an outlet. Let's say this, you have an outlet and you connect a voltmeter every 2 seconds to it. So you just plug, unplug, plug, and you get some dots, okay? You're getting samples from the voltage. Obviously, this is 50 hertz per second. You can measure that, but imagine that you're doing that 100 times per second. Then you're gonna have some points that follows the sinusoid of the outlet power, okay? So you're just getting samples from that. Now, the way that we convert a digital signal to an analog one is with a simple one way that there are dozens of ways to do it. But one way to do it is with a simple, what we call a envelope detector, okay? So an envelope detector, basically what does, it's like a capacitor. So the capacitor charges and then it takes time to discharge. And when you want to, it has a memory, I could say. This is the memory part of our circuit. So when you charge it at a certain point, because it's a large capacity, the capacitor, when you disconnect it, it takes a little bit of time to discharge, then immediately you charge it again to the next level. Okay, so that's one way to do it. You can use a simple capacitor to do it, and we call it an envelope detector because it creates an envelope over the signal. Okay, and this detector is actually the principle of an AM, what we call the amplitude modulation. Next semester, if you have communication system, you're going to learn about AM, FM, which are amplitude modulation and frequency modulation. And an AM system is basically, it has a carrier signal and the information signal, and the carrier signal is actually inside the information signal. And we just are interested in the shape or the envelope. And if you connect this to a diode, an op amp, and a speaker, you have a radio, an 8-in radio. Pretty simple to build. I don't want to go into details. That's topic for another course. So is this clear? Okay. So now that we learned how we can go from analog to digital, our main focus here is digital signals. Analog signals is for a different course. It's called Signals and System and Communication Systems and Analog Signal Processing. Let's see how we build these digital signals, how we make them and how we process. So a binary digital signal is an information variable represented by physical quantities, discrete quantities. For a digital system, the variable takes on discrete values. We have two-level or binary values are the most prevalent values. The binary values are represented abstractly by digits 0 and 1, words like false and true, words like low and high, and on and off. Binary values are represented by values or range of values of physical quantities. Again, you can read faster than I can. But in a digital system, we usually show them with different levels of voltage, okay? So here, let me erase this so you can see. So these are the notes from last year. Let me erase it so you can see better. So in this particular case, we can say 5 volts and 0 volts. So imagine you have a switch and that switch is connected to a battery, okay? So when the switch is closed, for example, V out when it's closed, V out would be 5 volts. When it's open, V out would be 0 volts. So you have on and off, okay? When it's on, we have a logic of 1, 5 volts. When it's off, we have a logic of 0. And usually we want to put a threshold, an undefined region between them. So the region between, usually we put an undefined region, and I'll explain why do we need this undefined region. So if we have a 0 and 5 system, anything below 3 and above 1 volt is in the undefined region. It's unacceptable. It's not the logic of 1 and not logic of 0. So here we have the logic of 1. Let me draw it with a different color. And here we have the logic of 0. 1 and 0. So this is a binary system. Binary means we have two levels, zeros and ones. Okay. Now, why do we need this undefined region? I'll explain in a bit. But before that, you may ask, why don't we use, instead of 0 and 5 volts for 0 and 1, why don't we use 0 and 1 volts? And there are some benefits to when we use 0 and 1 volts, or 0 and 0.5 volts, 0 volts and 0.5 volts. So 0 volts would be the logic of 0, 0.5 volts would be the logic of 1. So instead of 0 and 1 or 0 and 5, I can have 0 and 0.5 volts as our logics of 0 and 1. And by doing that, I have reduced my voltage by 10 times. And if this logic system is used in a phone, imagine if you can reduce the power of your phone 10 times, the power that the circuits consume. And in a CPU, you may have millions of logic gates. So millions of logic gates, you're reducing the voltage from 5 volts to 0.5. It's going to make a huge difference. So instead of your battery lasting 1 day, it's going to last a month. On top of that, because you're using a lower voltage system, it's going to generate less heat. Less heat means less loss, because as you know, when the temperature increases, the internal resistance increases as well. So you're going to have more loss. It's going to have a cascading effect. The battery is going to last longer. It's going to be cooler, and it's going to have a lot of benefits. But there's a big downside to that. So why don't we use 0 and 0.5 volts for our binary? Because when they are too close to each other, so this is 0.5 and this is 0 volts. Sometimes when we switch from 0.5 to 0, we have a situation what we call overshooting. And what happens is basically, I'm going to draw it bigger. When it goes, it's not as smooth as like a step. It actually shoots back, and actually in real world, it looks something like this. Okay, so we have a slope that we call the switch rate. And when it's too close, the computer can't actually differentiate between 0 and 1. We don't know where is 1 and where, because it's getting so close that we can't determine if this is the logic of 0 and 1. And then, therefore, we're going to have errors. Okay. So it's very important to fix this. We can make the gap wider. So instead of 0 and 0.5, we can have 0 and 1 volts, and then put an undefined region in the middle. So if the signal is in the middle, we say it's nor 1 nor 0. It's an error. It's nothing. It's not 0. It's not 1. So that's the reason we like to increase the voltage. But you may ask, why don't we do now on the other side? Why instead of 0 and 5, why don't we do 0, let's say, and 7.5? Just a little, so we are confident that we don't have any errors, because the higher the voltage, you're gonna probably have less errors. Why don't we go from 5 volts to 7.5 volts? It's not going to increase the power that much, maybe by 5%, something like that. But why do you think we don't go to 7 or 12 volts? Or actually, the first computers there are like 50 volts something. Then they went to 12 volts. Then they went to 5 volts, 3.5 volts, 2.7, and so on. They are lower now, 2.5 something. I think the phones are 2.5. I'm not sure. Double check it, but lower than 5 volts, definitely. So why don't we go to 7.5 volts?
5 is sufficient now.
5 is sufficient, but still we have some errors. We can make it better in terms of errors if we go a little higher. There's another problem as well when you go high. Imagine that I'm a signal and I'm bouncing between 0 and 1, okay? Is it easier and faster for me to bounce on these? And on the ground, so imagine the floor is 0, and when I go on this, it's gonna be 1. Is it easier for me to bounce on this and back, or is it easier for me to jump on the floor and on this? So definitely when you have a lower level difference, it's gonna be much, much faster, more efficient. One thing that is super important in computer is what we call a clock speed that you see on the CPUs. For example, they say the frequency of this is 3.5 gigahertz, okay? So 3.5 gigahertz, it means it can go from 0, it goes from 0 or switches from 0 to 1 and 1 to 0, 3.5 billion times a second. So that's 3.5 gigahertz. So the faster the clock speed is, the processing power is faster and higher, and it's much faster. And one thing that we know from Moore's law, we want to make it faster and cheaper. So we want to increase the frequency. Okay, we want to double the number of transistors to do more processing, and actually we want to do it faster. We have currently hit a ceiling on how fast the processor can process. We have limitations on these semiconductors. It's around 4.8 like gigahertz. Everything over that the physics doesn't allow it. I don't want to go into the details. It's part of electronics 3. It's the upper cutoff frequency. Technically, the transistors become short-circuited, so anything above that doesn't, at least for now. Future, they are working on these laser lights, transistors. They can, but that's a different story. Or quantum computing could be faster in theory. But in these semiconductors, we have these limitations. But again, we want to maximize our switching speed. We want to maximize our frequency and the frequency response. Therefore, we're going to have a faster system. So when you have a lower voltage, you have faster, more efficient, but you can't go too low because you need to have a undefined or a threshold between your upper level and the lower level. Okay. Does it make sense? Yes. Okay. Now that we learned about digital and binary signals, let me give you an example of where we use the digital signal. So as mentioned, one way is to use it in sound wave. By the way, this one that I spoke about, this has multi-levels. So instead of binary, we may have 10 levels. So this may have 10 levels, okay? A binary only has 2 levels, so zeros and ones and zeros and ones, okay? But if instead of 2 bits, we have 4 bits, you're gonna have 16 levels. If you have 10 bits, you're gonna have 1024 levels. So, and I'll explain more about this. Now, you may think, so this is sound 2 dimensions, for example, X and Y. What about if we have 3 dimensions? If we have an image, how do we show that with a binary system? Okay. So this is actually how, and this is actually from last year. An image, a digital image is represented, how we show a digital image, okay? So a digital image is showed by pixels, okay? Pixel is actually a Latin word. It's a combination of 2 words, picture element. They call it pixel, okay? Each pixel has 3 colors in it. For display, we usually have the RGB, red, green, blue system. And the RGB system, when we combine these 2 colors, we can build all the colors, okay? So for example, if one pixel, we have R, G, and B, all 3 colors turned on, when you combine all the colors, you're gonna have a white color in the output. So RGB, when they are turned on, all 3, you're gonna have a white color. When they are all turned off, you're gonna have a black color. when green and blue are turned off and red is turned on, you're gonna have a red color. And you could change the intensity as well. So green or red can go from the intensity of 0 to 10. 0 means the 0 voltage to the red LED means it's completely off. 10 means it's at its maximal level, maximum voltage. So it's the highest brightness. So you can change the intensity, the contrast, by changing the voltages of these 3 LEDs. Usually the newer TVs, they have LEDs. So you have 3 LEDs at the back. And it's the same in a camera, digital camera as well. So instead of having 3 LEDs, they would have 3 sensors, 3 RGB sensors that picks. The more pixels you have, you would have a higher quality, higher contrast, higher resolution. I'm sorry, higher resolution camera. So that's the reason a 10 megapixel camera has lower resolution than a 40 megapixel camera. So you can see the difference between different smartphone generations, okay, or digital cameras. But to put on a side note, resolution is just one part of the quality of the picture. Contrast and other signal and actually sensor quality and other things, the aperture is, you have different factors. So you may have a digital camera that is that 10 megapixel and the picture quality is greater than a smartphone that is 100 megapixel, because that sensor is built for that. You have higher contrast, meaning different levels of lighting and the lens, everything. There are a lot of factors into the quality. Doesn't necessarily mean if you have a 50 megapixel camera, the resolution is higher than 5, but it doesn't necessarily mean that the quality is higher than the 5 megapixels. And one other thing is, as you get further from the picture, you can't see the resolution unless you get very close. You can see the individual pixels or the pixelation. There's a difference between a 50 megapixel and 10 megapixel. But usually when you look at a distance above like 12, 14 megapixels, you don't see the difference that much. Okay. Now, you may ask, how do we set up different levels of voltage? We show that with a binary number, okay? And imagine 0 is 0, 0, 0, 0, 0, 0, 0, 10 zeros gives you 0 volts, and 10 ones gives you 1 volt. And if I have 9 zeros and a 1 gives me 1 volt, 9 zeros and 2 ones give me 2 volts, 9 zeros and 3 ones. These are different methods. Gives me 3 volts and so on. So therefore, I can put different levels on it as well. So instead of one level of voltage, I can put 0 volts, 1 volt, 2 volts, 3 volts, up to 100 volts if I want, okay? And if I put, for example, 5 volts, I have 50% light intensity. If I put 0, I have 0%. If I have 10, I have 100%. Does it make sense? It was exactly like what we had here. Instead of having 2 levels, I have multiple levels in a binary. And the more levels you have, you're gonna have a higher quality picture. So now, one of the important things that we need to learn before we get into decimal and binary numbers is the power of 2. So the power of 2, if n is 0, 2 to the power of 0 is going to be 1. If n is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, 2 to the power of 3 is 8, 2 to the power of 4 is 16, 2 to the power of 5 is 32, 64, 128, 256, 512, 124, 248, 496, 8,192, which is going to be 8,000 or 8 kilo. And so 1,024 is actually 1 kilobit, for example. Then 10 to the power of 20 is 1 mega, 2 to the power of 30 is 1 giga, and 2 to the power of 40 is 1 tera. These numbers may seem familiar for you. Where have you seen these before? In an iPhone, for example. When you want to buy an iPhone, all of them have the same CPU, but the difference in their price is the memory. You have an iPhone or an iPad or a phone, which is 256 or 512 or 1 gig, okay? These numbers are very important. First of all, try to memorize them because all the binary systems and the computer systems, computer architecture is based on these numbers. We usually have 2 megs of memory or 4 or 8 or 16 or 32. It's very unusual to have a 12 gig or a 13 gig or a 14 gig. Because if you want to build a 14 gig, you need a 8 gig and a 4 gig and a 2 gig, which is very difficult to, coordinate and connect. So when they build these memories, bulk memories, they are in the power of 2s, okay? So that's the reason in the iPhone, we have 1 gig, 2 gig, 4 gig. We don't have 3 gig. I haven't seen 3 gig or 1 meg, 10 meg, I'm sorry, 20, 1 meg, 2 meg, 4, 8, 16, 32, and so on. We don't have 20 meg or 24 or something like that. Okay. Now the number systems and the decimal, we're going to start with the decimal number systems. I think it's better to go into slideshow mode. Can be easier this way. Happened there? I don't know. Let me erase this. Sorry. This font. So I'm going to take you on a journey back to 4th grade elementary school. And we're going to start with decimal numbers. And then I'm going to go to binary numbers. So a decimal number, we have a base, which also is called a radix. So for a base of 10, we have 10 digits. Digits 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So 10 digits between 0 and 9. Between 0 and 9. The digit positions, we have the integer and the fraction. The digit weight, we have the weight is equal to the base power of the position. And the magnitude is the sum of the digit times the weight. Now let's solve a practical problem. So for example, if we have 512 70.74. So 512.74, we have 5 100s, 1 10, and 2 1s. And we have 7.1s and 4.01s, okay? So again, 5 100s, you can see on top 5 100s. And what is our base? Our base is 10, okay? So we're going to start with the fraction. And the first digit is going to be 10 in the power of 0. Second one is going to be 10 in the power of 1. Third one is going to be 10 in the power of 2. And for the fraction part, the integer part is 10 to the power of 0, 1, and 10 to the power of 2. The fraction, we're going to have 10 in the power of negative 1, 10 in the power of negative 2. 10 in the power of 2 is 100. 10 in the power of 1 is 10. 10 in the power of 0 is 1. 10 in the power of negative 1 is 0.1, and 10 in the power of negative 2 is 0.01. Now we would multiply them by the weight, and we're going to get the answer. So for example, here, we're going to have I'm sorry, let's go back. We're gonna have 5 times 100. 5 and 1 times 10 and 2 times 1. 10 in the power of 0 is 1. So this is 10 in the power of 0, 10 in the power of 1, 10 in the power of 2. And we would have 7 times 0.1 and 4 times 0.01. And when we add all of them together, we have 512.74. Now let's solve another one. Imagine we have, give me a number between 1 and 10,000.
175.3.
I'm sorry, 675.3. So if I want to convert this, I'm going to have 6 times 10 in the power of 2. Am I correct? Plus 7 times 10 in the power of 1. Plus 5 times 10 in the power of 0. Plus 3 times 10 in the power of negative 1. So it's going to be 600 plus 70 plus 5 plus 0.3, which is going to be 675.3. So again, we start with the fraction point, and to the left, it's going to be base in a power of 0, 1, 2, 3, 4, etc. And on the right is going to be the base in the power of negative 1, base in the power of negative 2, and so on. I have an example here from last year, 4,679.36. It's going to be 4 times 10 in the power of 3. Sorry, this is power of 3. 10 in the power of 3, 10 in the power of 2, so on. Plus 6 times 10 in the power of 2, plus 7 times 10 in the power of 1, plus 9 times 10 in the power of 0, plus 3 times 10 in the power of negative 1, plus 6 times 10 in the power of negative 2. And when you add them together, you're going to have 4,679.36. Now let's do the base of 8. So we did the base of 10, which is decimal. You're all familiar with. You learned it in elementary school. So for different bases, base of 8, the digits are between 0 and 7. You have 8 digits, which is 0, 1, 2, 3, 4, 5, 6, and 7. So the digits are between 0 and 7. 8 digits. Now, again, the weights are equal to the base in the power of their position. Again, the first position, 10 in the power of 0. It's got 8 in the power of 0, 1, 2, and so on. And the magnitude is going to be the sum of the digit times the weight. And the formal notation, let's go back. It's going to look like this. So this is an example of a base of 8. We have 512.74. So the first digit is going to be 8 in the power of 0, 8 in the power of 1, 8 in the power of 2. 8 in the power of negative 1, 8 in the power of negative 2. So 512.74. If I multiply it in the base of 8, it's going to be 5 times 8 in the power of 2 plus 1 times 8 in the power of 1 plus 2 times 8 in the power of 0 plus 7 times 8 in the power of negative 1 plus 4 times 8 in the power of negative 2. So when we add them together, 5 times 64, it's going to give us 320, plus 8 plus 2, it's going to give us 330, and 7 times 10 in the power of 8 in the power of negative 1 plus 4 times 8 in the power of negative 2, and when you add them, it's going to give us 0.9375. So this number is equal to 330.9375 in the base of 10, but in base of 8, it gives us 512 or 512. It's not 512, it's 512.74. Now let's solve an example. I'm going to give this as a quick practice to you. So I have the number 10 in the base of 8. What is this number in the base of 10? So 10, the first digit is going to be multiplied 0 times 8 in the power of 0 plus 1 times 8 in the power of 1. So 10 would give us 8 plus 0, which is 8. So 10 in the base of 10 is actually 8. So when you write the base of 8, after 7, you're going to have 10. Then you have 1, then you have 1, 2, so on. You don't have 8, number 8. The digit 8, you don't have it. After 7, you're going to have, after that, you're going to have 10, which is 8, 1 is 9, 1, 2 is 10, and so on. And a octal number. So I think it's, let me do one more practice and then we can wrap it up. So can you give me a 3-digit number? Anyone? So 214 in the base of 8, we want to convert it to the base of 10. I'll give you 5 minutes to solve this. So 214 in the base of 8, we want to convert it to base of 10. What is the answer? Did anyone have the answer? So it's gonna be 2 times 8 to the power of 2 plus 1 times 8 to the power of 1 plus 4 times 8 to the power of 0. Yes, 2 times 64 plus 1 times 8 plus 4 times 1. 2 times 64 is 128 plus 8 plus 4. So it's going to be 140. Am I correct? Did you get the same answer? Yes? Okay, 140. So it's 140 and 10. So I would send some practice problems and hope the first homework is going to be just about these. This is it for today. We're going to have a small quiz for ourselves. For the online students, I'll post another quiz.